Okay, in the last lesson, we took a look at vertical asymptotes. For this lesson, we're going to look at horizontal asymptotes. So, horizontal asymptotes exist when the value of x approaches either negative infinity or positive infinity, and the value of f of x approaches a certain value, which we're just going to call capital L. To determine where a horizontal asymptote exists, we consider the following. If y is equal to L is a horizontal asymptote on the curve y equals f of x, this occurs if either the limit as x approaches negative infinity for f of x is equal to L, or if the limit as x approaches positive infinity for f of x is equal to L. So it doesn't actually have to exist for both of them, it could just exist for one of the cases. There are many possible ways for a curve to approach a horizontal asymptote. So if I had the asymptote at y is equal to L, then I could have it where it's going to approach the asymptote as x is approaching positive infinity, or limit as x approaches positive infinity for f of x is equal to L from beneath. We could also have it where it could approach from above. Once again, if I say this is y is equal to L, then I could have it approaching L from positive infinity from above L, or the limit as x approaches positive infinity for f of x is equal to L on the positive side. We could have it where it is just getting closer and closer to L, but is actually oscillating above and below. So it's not necessarily approaching from the top side or the bottom side. It's approaching L over and over and over again, oscillating, where we just say that the limit as x approaches positive infinity for f of x is just equal to L. It's coming from the positive side and the negative side. We could have it approach negative infinity for x. Where it could approach from below, or it could approach from above, or the limit as x approaches negative infinity for f of x is equal to L from below, or the limit as x approaches negative infinity for f of x is L from above. We can also have cases where we could have two separate asymptotes. So I could say that y is equal to L1 and y is equal to L2, where it could approach one of them as it approaches positive infinity, and it could approach one of them as it approaches negative infinity. And so now we have a split one, where we'd say that the limit as x approaches negative infinity for f of x is L2 from above, and the limit as x approaches positive infinity for f of x is L1 from below. Now, obviously, this is not all the different possibilities, but there's so many different ways that it could approach these horizontal asymptotes. All right, we need to recall the following properties of limits. the limit as n approaches positive infinity for 1 over n to the power of r is going to equal 0 so long as r is greater than 0. Remember that we thought of this in terms of 1 over n to the power of r, or 1 over infinity to the power of r, is going to be 1 over a very big positive number. And as my denominator gets bigger and bigger and bigger, this is going to approach the value of 0, because we know that we can't actually substitute the value of infinity in. We also know that the limit as n approaches positive infinity for r to the power of n is going to equal 0 if the absolute value of r is less than 1, or if negative 1 is less than r, which is less than 1, knowing that r cannot equal 0. So if I had something like r is equal to 1 over 2, for an example, then in this case, it would be 1 over 2 to the power of infinity. Well, 1 to the power of infinity is just going to be 1. And I'm going to have 2 to the power of infinity, which is going to be an ever-increasing denominator again, like our last example, and that's going to get closer and closer to 0. So for example 1, it says, given f of x is equal to 1 over x, find the limit as x approaches negative infinity for f of x, and the limit as x approaches positive infinity for f of x. So let's start with the negative one first. If we take the limit as x approaches negative infinity for 1 over x, then that means that I'm going to be trying to take the limit as x approaches negative infinity for 1 over a very big negative number. This is going to approach 0, but it's going to approach 0 from below, because I'm doing it for a negative number. So it's still going to be approaching 0, but it's going to be approaching 0 from down here. If I have the limit as x approaches positive infinity for 1 over x, then that's going to be the limit as x approaches positive infinity for 1 over a positive very big number, which is still going to approach 0, but it's going to approach 0 from the positive side, which would exist up here.